Okay, so today's problem is maximum depth of a binary tree. So given the root of a binary tree, we need to return its maximum depth, which is the longest path from the root down to any leaf node. So for example, here our answer is 3 because we start at the root node of 3, and the longest path is either going from 3 to 20 to 7, which is 3 nodes, or 3 to 20 to 15. And we don't care between each one. We just want to know what is the longest length. Another example here is 1 null 2, which is just 1 and then there's nothing on the left side and 2 on the right side. So that would be too high. Or too deep, sorry, that's how it's framed. And it is possible that we have no nodes in the tree. Does that make sense to everybody? Any questions so far? Okay. So to do this, we can store some kind of max out here. And I'll just say m equals 0. And starting from the top of the tree, we're counting depths instead of heights, so it's fairly straightforward. So we visit this parent node, and we add 1. So if we have 0, or just nothing in the tree, we'd have no tree at all. So our height would be 0. But starting here, we add 1. We've seen 1 node along this path. And then for here, let's say we go left next. Then this becomes 2. And this is also 2. And going further down, this is 3 deep, and this is 3 deep as well. So to do this, we just need to store each node and its depth. And once we see it again, we can change our maximum. So starting out here, we have 1, that makes a new max. And then here and here, we have 2. And then here we have 3. So we're pretty free to do whatever we want to do to traverse the tree, but I'm going to go with DFS. So we're going to do a pre-order traversal, which just means we're going to start at visit the root node, then the left nodes, then the right nodes. It wouldn't matter if we visited the left or right first, but we do want to visit this parent node first to be able to get the depths. We could also do BFS if we wanted to, just do level by level. So we have this node and these nodes and just count the amount of levels we have. But I'm just going to go with DFS. Any questions? Cool. Gonna copy this again so we can start over and just show off how we would do that exactly. So to get these answers, I'm just going to store, I'm going to make a stack of all the nodes we need to go through and their depths. So starting out here, we're going to push on this 3 to the stack. If it's null, or the root is null, we would just return the max, which starts at 0. But it isn't in this case, so we're going to push on this value. So we would have our node, which is 3, and the depth, which is 1. And then we pop off from the stack. We see a new max, which is 1. And we get each of its child nodes. So we get the left and the right. If we want the left node to be visited first, we would push the right, then the left. Here it doesn't particularly matter, but I'm going to go with that anyway for consistency. So we have this as 1. We're going to push on this right one. We're going to push on. Sorry, we're going to push on the. Oh, yeah, we're pushing on the right first. So we do 20, which has a depth of 2, which is just this depth plus 1. And then we're also going to push on 9, also with a depth of 2. Then since we're doing DFS, we're going to go for this one, pop it off. We have a new maximum. So update that. And then we're going to check both of its children. They're both null, so we're not going to push anything else back on. And move on. We still have more things in our stack to go through. So we're going to pop this one off. There's no new max, so we don't do anything much here. And then we check and push on our right then left nodes with their new heights. So we have 7 and 15. We're going to push on 15 first, or 7 first, sorry. Push on 7, and then we have a depth of 3 for this node. And then push on 15, which also has a depth of 3. And then we will pop both of these off. 15 gives us 3, which is a new max. And then 7, or there's no nodes to push on, so we're just going to leave it at that. And then for 7, the same thing is true. There's no new max, so we don't do anything with the max. And finally, there's no more children, so we're not going to push any more on. If there were more children, we would go deeper, but this is a 3 deep tree. And then we finally return 3. We do have to go down every single path in case that it's deeper on one side. So we can't say this is 2, so it's not worth anything, because we could have 7, 8, go down even deeper, 3, 4. Any questions?
Yeah. So after each level, do you pop off both nodes, or each node on that level, and then go on to the next child?
Since we're doing DFS, we go over one node, or we go over them more greedily. Like once we see a new node, we're going to go after it immediately. So we start out here, and then we start going down this left path all the way to the bottom. And then once that left path is all the way used up, then we go down a right path, and then all those left paths. And then we go down a right paths, all the left paths, and then finally all the right paths.
So you just continue going down all left paths until it has no more children, and then you pop off.
Yep, we're visiting the parent nodes, then the left nodes, then the right nodes.
Okay, I get that.
The only important part is that we visit the parent nodes first, and then after that, you could do whatever you want. We could do it level-based traversal, or we could do it right nodes, then left nodes, and either one works. That makes sense?
Yes, it is. Thanks.
Cool. Yeah, then let's get into coding it. And if we have time, we'll do both DFS and BFS. Okay. So to handle our first case, or our edge case, where our root is null, we want to just return 0 because the depth is 0. And then in our other cases, we want to iterate through. So our stack, like I said, is going to have tree nodes as well as depths. So our stack is a tuple of nodes and tree nodes. So we're going to initialize this as the root, which we now know is a tree node, and a depth, which this is a depth of 1. And then while our stack is not empty, so while the length is more than 1, or more than 0, sorry, we are going to pop off the stack. So our node and our depth is equal to stack.pop. And then we check for new max here. And here we're going to push our nodes. And finally down here we're going to return the max. So we should get that done first. So let's go for returning the max first before pushing more nodes. So max is equal to 0. So then our max is equal to math.max, max or the depth. Let's call this max depth to be a little more descriptive.
Why is our max depth starting at 0 and not 1?
It very well could start at 1. Doesn't really matter.
Okay.
At this point, we will always loop at least once just because it's in there. But good point. We could do either one. We could also move max depth up to the top and then just return max depth. But I like not having to worry about a variable all the way to the top of our function. So style pretty much. And then for our nodes here. Oh, sorry, any more questions?
Nope, that's all.
Cool. So to push our nodes, we need to check to see if they're null. So if node.left is equal to null, or is not equal to null actually. So if it's not equal to null, we are going to push it on. So we push node.left as well as depth plus 1. We shouldn't have pushed to the node, we should push to the stack. And then since we're doing pre-order to go left then right, we want this one up here to be right. But ultimately it does not matter. And this should be everything we need, I believe. Any questions? Cool. Let's see if it works. Looks good. Yep, it works. The time complexity of this solution is O of n, where n is the number of nodes in our tree. So the more nodes we have, the more nodes we need to traverse. We have to look through every single node, no matter what, and we only iterate over the tree one time. And then the size of the stack is going to be O of log n, I believe, at max, because we're going through the whole height of the tree. Well, assuming it's balanced. If it's imbalanced, then it could be O of n as well. So imagine we have a tree that looks like this, like 1, 2, 3. Then we could possibly have the whole thing on here. So O of n, worst case, space, and then O of n, worst case, time as well.
That
I think somebody said something.
Somebody just hopped in and hopped back out. I
Oh.
think they're fine.
Okay. Cool. Everybody understand time complexity and space complexity? Any questions? Cool. So a separate approach, since we have time, would be a BFS approach. I'll just use this since we already built it out. So we would go through each level, and we wouldn't necessarily need to store the depths at this point. We could store one global depth and then loop through everything in the level. So if we do a BFS approach, instead of using a stack, we'd use a queue. So we would NQ and DQ. So we would take from one side, NQ from the left side, and then DQ from the right side. Or the other way around, if you want to think about it like that, both work. Instead of pushing and popping onto one specific side. So starting here, I'm going to put it on the right side just for that. Well, yeah, let's just leave it here. So we have 1, and then since there's no more in this level, this is level 1. We can pop that off, or not pop it off, sorry, DQ it, and then push on, or not push on, in queue 2 and 4 for that level. Maybe let's add a 6 here too. And then once we go through this level, we go DQ this 4, and then push its children onto a new queue. Or sorry, enqueue it on the new queue. 6 and 5. And then finally go through 2, push or enqueue all of its children. I'm not sure why I can't use the correct terminology today. And then finally, for the last row of depth 3, we would DQ all of its children. And then if there's any more child nodes to go through, we would go through them. But at this point, we have 3. And none of these have any children, so we go through 6. C has no children, 5 has no children, 3 has no children. So there's nothing else to add to our queue. And we're done. We don't actually need to create a new queue. I just did it for the example, but we could count how many parents are in each level. So like we have 1, for example, here. So we start out with 1, and then the length of this level is 1. So we do a for loop with 1 and dequeue that many items. So we dequeue 1, and we enqueue 2 and 4. And then here, since we've gone through the appropriate amount, we've done 1 iteration, we can go down here, iterate 2 times, dequeue our 4, enqueue its children, 5 and 6, and then finally dequeue this 2, and enqueue this 3. And now since we've done 2 iterations, we're now done with this level, and we're on to our final iteration of depth 3 with 3 elements, and do that same process all over again. Dequeue 6, 5, and 3, add all of its children and queue them, and then continue on if there's more, but otherwise, no. Does that make sense? Any questions? Cool. Then let's code that one out. So instead of a stack, we have a queue. And we no longer need to worry about a global depth. Our max depth is 1. And instead of popping, I believe we're going to unshift. I always mix it up, so we will see. Unshift inserts a new one, so it's actually shift. So we shift a new element. Instead of checking for a new max, we just know we're at a new max. So max depth plus equals 1. We need to store our length up here. So our length is equal to queue.length, and do a for loop for that many. Or maybe a while loop, but either works. We can do length. We don't need this piece either. So in here, we're actually going to do this logic. Our node is the shift element and push both of its children. Oh, okay, yeah, we need to push just the children and not the actual. Yep. Any questions for this one, this approach? Oh, I forgot. Oh, no, we're still pushing. Yeah, that works. Yeah. So let's see. One thing I'm thinking about is it could be 1 off if we start at 1 here, because that would be completing a level and then adding 1. So once we go over the first level, we've incremented to 1. We'll see though. Yep, we're 1 off because we should start at 0. And I can just change it here. And looks like it works. Nice. Any questions for this approach? The time complexity is still O(n). We still have to go over every single node. We still... maybe the space complexity could be a little bit different now that I'm thinking about it, because we could possibly have the maximum amount on a level, which I believe is n to the level divided by, or it's 2 to the level possibly. What would it be? This level we have 1. Here we have 2 and 3. And then here we have a maximum of 2 or 4. So this one is 2 to the 0, and this one's 2 to the 1, and 2 to the 2, and this one could have 8. Yeah, so we could say time complex or space complexity is 2 to the 2 to the h maybe, where h is the height of the tree. So if it's too tall, then it's possible you have 4 on the stack at any one time, or 4 in the queue, sorry. Cool. Any questions on this one? Okay, let's run through an example with this code. Let's do 1, 2, 4, 5, 6, like that. So we start out, check if our root is null. It's not null. So then we initialize our max height in our queue. Our queue starts out with this root node of 1. Well, our queue length is greater than 0. We're going to store our length, which is currently 1, and go over this whole thing. So here we need to do one iteration. So we dequeue this 1, check its 2 child nodes, and enqueue them if they're not null. So we enqueue 4 and 2, and we can say at this point, max depth is 1. And on to the next loop, our queue length is greater than 0. So we are going to traverse the level. So the length of this is 2. So we're going to do 2 iterations. So first we dequeue our 4, and then enqueue 6 and 5. And then dequeue 2, push on its children, which don't exist. And since we've done 2 iterations, we're going to go down to the max depth and increment it. So we have 2. And then we still have things in our queue left, so we're going to iterate over the last level. So we check 6, we dequeue it, and enqueue its children, which don't exist. So we enqueue nothing. And then we do the same for 5. We dequeue it and then check its children, which also don't exist, so we don't enqueue anything. And finally, increase our maximum depth to 3. And if we verify in this tree, the maximum depth is 3, either going from 146 or 145. Any questions? Cool. Let's go over the other approach as well. The DFS approach. So here, if our root's null, it's not null. So we move on, we create a stack with a tree node and a depth. So our tree node is 1, and it has a depth of 1. And then we initialize max depth as 1. And while our stack isn't empty, we're going to pop off the stack. So we pop off this one, our node is 1 and our depth is 1. We get the max between max depth and the depth, which is still 1, so we don't do anything. Then we push on the child nodes. So first we go to the right, push on 4, and depth was 1, and our depth was 1, so we push on 2. And then we push on 2 with a depth of 2 as well. Then going back over, stack still exists, or our stack isn't empty, sorry. And we pop off a node and a depth. So we pop off this 2 and 2. We set a new max depth, which is now 2. And we push on children if they exist. And in this case, neither exists, so we don't push any on. And move on to the next loop. Still have an element in our stack. We pop it off. The max depth is still 2. And we check its child nodes, 5 and 6. They both exist, so we're going to push them on. Push on the right one first, then the left one. So we have 6 and depth plus 2, or depth plus 1, which is 2. or our depth is 2 and we're adding 1, so we get 3, sorry. And the same thing for this one. We have 5 and their depth is 2 plus 1. 5 and 3. And we go to the next iteration. Stack length is still more than 0. So we pop off a node. We have a new max because our max depth is 2 and we just found a 3. And then we check its children to see if they can be pushed on. And for 5, there are no children, so we push on nothing and move on to the next loop. We still have one final element in here. We pop it off. 3 is equal to 3, so max depth is now 3. And we push on its children, which are non-existent. And then finally go to the end of the loop. Stack.length is not more than 0, it's equal to 0. So we end off and return our max depth, which is 3. Any final questions? I'm going to put the code in the chat. Okay, I don't hear any more questions, so I'm going to end the recording here. Oh, I see someone typing. I did not do it recursively, but I can do it recursively. But I might struggle a little bit. So let's try it recursively as well. So instead of an explicit stack, we're going to want to return our values. So we don't need, oh, this is the queue version. I want the stack version. So we don't need an explicit stack or max depth or this while loop. A lot of this goes away. So we have a left height. That would be max depth. And we pass it root dot left. And then a right height. And then we just need to return the max of the two, I believe. And let's see if that works. That's not the correct thing. I did not copy that correctly. Let's try that again. Oh, okay, because I pasted in multiple of them. There we go. Looks like we did something wrong. Oh, I forgot our +1. Looks good to me. I just forgot the part where we add on the current node. I just left it 0 forever. Yep, there's the recursive version. How do we decide whether you want to do something while traversing down or return up from the call stack? I always do it iteratively, so I don't have to worry about that one. But in this case, we are specifically mentioning we're doing depths. So the way they phrase the problem is we want to get each depth. So here we just say until we go down to hit null. Once we hit null, we're going to return 0 and then start adding on all the way back up and get the maximum of each subtree. But I would say just like this problem, we don't care about doing anything on the way up because we just care about the depth. So at this point, the depth is 1, and here it's 2, and here it's 3. So we don't worry about whatever's happening. You could do it the other way up and do it height-wise, but that's just a little bit more complicated. Here either works. I think it's conceptually easier with a BFS because you just go through each level and then at the end it's the number of levels you ran through. But it's different for every person because I don't like recursion that much, but other people really like recursion. Cool. Any more questions? Okay. Gonna end the recording there then.